Hi, this is a question from the PSN Edexcel Year 1 Pure Book. It's exercise 12J and it's question 2. I've got the question on the screen for you, and I'm going to go through this one. So, sketch the graph of this. Well, we need intercepts, we need maximum points, we need minimum points, so let's go ahead and find all of that. I know my intercepts I can tell straight away from here, so I know my x-intercepts, they're going to be x equals -1 and x equals to 4, and we're going to have that twice, so that's going to be one of our minimum points actually. If you think about how the graph would look, that would be one of our minimum points. So to find our stationary points, put that as SP, stationary points, I'm going to need to expand these brackets and I'm going to need to differentiate. So I'm just going to expand the brackets for us. So you can check that you can do this yourself, but this is what you would get if you were to expand these. And then when I differentiate, I am going to get 3x squared minus 14x plus 8, and then when I factorize that to find the solutions to this, because when I want the stationary points, I need to set it equal to 0. So when I factorize that, it's going to go like this. So x equals to 2 over 3. And x equals to 4. Corresponding y values for this, we're going to substitute it back again into the original. Never back into the differentiated forms, always back into the original when you're finding a y value. And we're going to get a horrible fraction again, 500 over 27. And then y equals 0. Well, we expected this one. These coordinates there are the minimum point, like I said before. So, going to draw this graph, I know what I've got to do for part B, so I'm going to try and set this up nicely. So this is my graph for part A, so I'm going to have to draw this. So, let's first put a little cross on my intercept, so -1, 0. Another intercept, well, we've got a double intercept here at 4, 0. That's also a stationary point. I can tell that's a minimum just by the shape of the graph. And we've got 2 over 3 and 500 over 27. By the nature of the graph, I know that's a maximum point. I can always double check that by finding the second differential, and at the point when you sub in x is 2 over 3, you would see that it would be negative. It would be a negative second differential. So, drawing the graph in a different colour, it's going to go up, down, touch the graph and go up. And it's an x-cubed graph, so that just makes sense that it would look like that. Okay, part B is asking us to draw the differential graph. I should really be labelling up my axes, shouldn't I? X. Then this wouldn't be y, it would be dy by dx, and that would still be x. So we could actually just sketch this graph here, because we've done that, but why don't we use the skill of being able to draw this without that? Because that's pretty much what we'll be expected to do most of the time. So if I get my little dotted lines, and I'm going to do it in a bit of a harmless colour, I need to connect my, well, I know where it's a stationary point, that's where my gradient is going to be 0. So I'm going to have a coordinate that goes there on the axis. And same for this one. So back onto here. So I know, in a different colour, I'm going to have 2 points there and there, because gradient equals 0, so it will be 0 on my gradient graph. Having a little think, about this? Well, we've got a positive gradient there. It's going to be slightly less positive, and then it's going to 0. It's negative, then it's more negative, then it stays negative, then it gets less negative here as it starts to curve back round, and then we go positive and positive. So if I quickly kind of have a think of a plot of how these would be, positive, then around this stage it's going to be less positive, then I said around this stage it's going to be negative, said it's going to get a little bit more negative here, it's going to get less negative on this stage, so bringing it closer back to 0, because if we think about this scale, it would be like -4 down here and -2 up there, so it's less negative. And then we go positive, positive. So doing your best attempt at a... bloody hell, better than mine. Ooh, that's awful. Scrap that. Best attempt at a sketch. That'll have to do. That'll have to do. I'm not going to sit here all day and draw curves when you know what I'm actually trying to do. Okay, so it's easier on a pen and paper than it is on what I'm drawing on here. But anyway, that would be our graph. And we could label up these axes 2/3, and 4/0. You could just tell straight from here that that's what you'd have been drawing anyway. So you can see this method is good. It saves us having to do all this if we didn't do it in the question before, and if you get a really gross one like an x to the 4, you don't want to be knowing how to draw the differential graph of that. So question 3 show that we've actually done that here. We've actually done that in these 2 steps, so we're not going to do that again. And part D is actually quite a simple question because we've done the most of it. Find where the differential graph cuts the coordinate axes. By doing it this way, well, we know it's there and there, so the x-axis cuts the x-axis at 230 and 40, and it cuts the y-axis when x is 0. So what would y be when x is 0? It would be 8. So there we go. Them last 2 parts was a nice and simple end. So yeah, that's that question.